Today we're talking about congruence and transformations. And this is no big step from where we have been. We've been talking about rigid transformations and rigid motion for a long time now. So we're just going to be putting these things together. So first of all, only write what you need to on this slide. These are your notes. Whatever you need to write to make sense is what you should be writing down. But two figures are congruent if and only if there is a rigid transformation or composition of rigid transformations that maps one figure onto the other. Okay? They get to be congruent if there's translations, reflections, or rotations that take one to the other. Yes. Sorry. Okay. So these are your notes. Write them so that they make sense to you. A rigid motion is a transformation that is either a translation, a rotation, or a reflection. The three things that we've been practicing thus far. It preserves their size, their shape, their angle measures. There's no getting larger, smaller. Everything's consistent. And that's why these things are congruent. So if we look at these figures, trapezoid, 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 if my image isn't being skewed by the projector, these three should be congruent to each other. But it's obvious that these three triangles are not. These two look like they could be similar, but this one's much larger than this one. So these transformations will preserve their size, shape, and angle measures. Okay? So we're trying to figure out if there are any congruent figures below. Okay? Are there any congruent figures in our drawing? Yes, it looks like there are. Okay, so what's an example of one of them? LKM. So triangle LKM is congruent to triangle. So here's LKM. And I like how Brandon said that. He said TSU. TSU. It may have been luck, but he said that perfectly. Why is it TSU if it's LKM? Because they're reflected. Very good. Okay. This is a reflection, so we want to make sure that we talk about L and T. If we say L first, we have to say T first. If we say K second, then we have to say S second, because that's the corresponding point in that reflection. And if we say M third, then we have to say U third, because the order matters. Are you okay with that? Okay, so that was one triangle. What's another pair of figures that are congruent? IHGJ. Okay, that's a rectangle. We don't have a symbol for rectangle, so we're going to write the word rectangle. IHGJ, congruent to. Okay, so Andrew, you started us with this. IHGJ, so QPNR, I would agree. QPNR. Can you see that those are corresponding angles? Those vertices are the same? Yes, sir. Good question. We don't have a symbol for it. And rectangle is a long word to write. And quadrilateral is a long word to write. But unfortunately, we don't have, what's that? Yeah, RECT. I would accept that. Okay. Quad for quadrilateral would be okay. Okay? Now, okay, listen up, guys. Shh. So what Andrew's saying here is because he said it in the order that he did, that this is a translation down 1, 2, 3, 4, 5, 6 units. Okay? For the sake of argument, could I have said that IHGJ is the same as RNPQ? Is it this RNPQ? Is it out of order? I would agree. I'm not crazy about it like that. But could this be a reflection across this line? I don't want to confuse you, but I want to show you that it could map it. There's another translation that could map it down there. Gentlemen. There's another transformation that could map this down there, and that's a reflection. So if someone else has an alternate answer, it could be completely right. Because this could be a reflection, or it could be a translation, and that's okay. Rectangles are not as picky as triangles, are they? Because they have 4 equal angles and 2 pairs of sides that are equal, so you could talk about them in a different order. Okay, last one. Here we go. We haven't talked about triangle ABC yet. So triangle ABC. Look at your image or the picture up on the board. If I say ABC, which way do I have to do it? D, E, F. Why? And remember that I've scaled this from my laptop to this, so they could be out of filter kilter. Look at your actual drawing. Okay. So DEF. Why is it DEF? What kind of a translation? A rotation of 90 degrees. And we can be sure so this is a rotation, we think, 90 degrees counterclockwise. Let's verify the points just to be sure. What did our rule say if we were rotating 90 degrees counterclockwise? AB went where? Well, let's make sure so we can see that it goes both ways. AB went where for a 90 degree counterclockwise? Negative BA. So if you have that memorized, that can help you this way too. So let's check. We think that C at 2, 1, what might be translated, rotated 90 degrees clockwise to F at negative 1, 2. Does it work? Yes. Okay. We think that A at 5, 1 might be a translation to D, a rotation to D at negative 1, 5. Absolutely. So this is these not looking quite right is a factor of the projector, not of the actual movement of those figures. Okay? Okay, next slide. Here's the next figure. How can we talk about this one? It's a rigid transformation or composition. It's a congruent transformation. What did we do to quadrilateral ABCD to get quadrilateral EFGH? Okay. Some are saying rotate 180 degrees about the origin. Okay, you could check your points and be sure, or rotate it on your paper and see. Others are saying it's a reflection across the line, the y-axis. And then translated down. It would be translated down 1, 2, 3, 4 units. Both are right. Okay? Both are correct. So there's more than one right answer to this. Okay? Everybody cool with that? Okay, next slide. Oh, sorry. Yep, I'm sorry. Trying to keep things moving. Andrew, face forward, please. Yeah, second one, sorry. Reflection across the y-axis, translated down 4. Okay? Reflection across the y-axis, translated down 4, or rotate 180 degrees about the origin. Translated, yep. Sorry for my... Either one is right. You do not have to give me both answers. Okay? Alex, face forward, please. Okay? Everybody ready? All right, next slide. Describe a congruence transformation that maps quadrilateral ABCD to quadrilateral PQRS. Andrew, face forward, please. Okay. ABCD. A is going to P. B is going to Q. C is going to R. And D is going to S. What is it? -90-degree rotation. Okay, 90-degree rotation about the origin. You should, because that's where it's moving. Okay. Good question, and I haven't seen any. I gave you an example of one a couple days back, but we haven't done any work with that, so probably not. Okay. Good question. Do we need to say? Shh, listen up, guys. Please. Do we need to say clockwise or counterclockwise? This one from A to, it is counterclockwise, right? So unless we say otherwise, we are assuming counterclockwise. Okay? Clockwise is this way. But these are moving in the opposite direction, so this is counterclockwise, and that's what we're assuming from here, or everywhere. Okay? Michael and Riley. Okay, reflections in a parallel, across parallel lines. Nitty-gritty, quick and to the point. We could have you do this. I tried to get to the labs to get GeoGebra and a laptop for you to do this, but the research papers are obviously going on. There are no laptops available right now. So, show you what it looks like. If I take a triangle and I reflect it across a line. So here is my original triangle. I reflected it across a line. Exactly what we expect, right? A mirror image of it. Then I reflected across another line that's parallel to the first. and I get a mirror image of the second triangle, right? Ignoring the middle one in between, what does this look like? A slide, a translation, okay? All I did was moved it. Two reflections across parallel lines is nothing more than a slide, a transformation, a translation, okay? Everybody cool with that? Easy enough? Okay. So the only distinction here is if this was my original figure, I moved it, I reflected it to here, and I reflected it again to here. This distance between these two, the distance between these lines, is half of the distance between these 2 points. So whatever this distance between these 2 lines is, you double it to find out how far it is between A to A double prime. Well, we reflected it twice, didn't we? So whatever distance we had once, we have again. So the total distance is 2 of my original. Okay? Okay. So here we go. Here's our next figure. We have PQ, P prime, Q prime, P double prime, Q double prime, reflected across parallel lines. They tell us that PJ, the distance between P and J, is 3, and the distance between L and P prime is 8. So the first question they ask us is, what are segments that are congruent to segment PQ? P prime, Q prime, I agree. Those are congruent. Good. Easy, right? Okay. How about PJ? What's going to be congruent to PJ? Here's the distance between P and J. The distance between P and J, P prime and J. Should be on your paper. There's not a lot of space to write. Yeah, I don't have it in that order. I just have the 3 listed. So you just have to write right below that. Name the segments congruent to PQ, PJ, and QK. So right in here. Okay. Finally, how about QK? Yes, sir. The J is right here. It's hard to see. There's no point for it because whenever we have a, okay. So QK, how about QK? The distance between Q and K, what's that going to be equal to? Q prime K. Okay. What do you think? Does JK have to be equal to LM? JK. This one right here. LM. Because they have to be, those are parallel lines. We have a 90-degree angle here. 90-degree angle here means this is 90 degrees, right? 2 straight angles, linear pair, perpendicular form. And so, yes, this is a rectangle, isn't it? And since this one you said was equal to this is equal to this, and vice versa, we should have a rectangle here. Okay. What's the length of P to P double prime? Or sorry, P prime to sorry. What is the distance between P prime to P double prime? 16. Why? LP. Good. This one is equal to this one. So this is 3. Okay. Then we've got 8 and 8. So if we wanted the whole distance, we could add them all up too. Okay. Okay. All right. So a couple more slides and we're done. Reflections across intersecting lines. Reflections across intersecting lines are a little different. If they're parallel lines, it ends up being a translation. If they're intersecting lines, what does it end up being? From ABC to A double prime, B double prime, C double prime that I've got up here. It's a rotation. It's not a 90-degree rotation that I've got here or a 180. This happened to be 31 degrees between those intersecting lines. So a total of 62 degrees rotation of these, the starting, the pre-image and the final image. Okay, that's okay, but let me show you. Okay, if I take, if you move a desk anymore, you can go to the office and talk to the principal about it. There's no reason to move my furniture. Taking AB. And we're reflecting it across this line to A prime, B prime. The distance that is being reflected when we reflect it one more time over across, this is a total of x degrees between these two angles. So the full rotation is going to be 2x degrees for the whole rotation. Okay? 2 reflections across intersecting lines becomes a rotation. And it's doubled the original angle between those 2 lines that are intersecting. Okay? So let's see an application of it. Here's a flag. The blue flag was the pre-image. It was reflected across line K. And K intersects with M. That second flag, F prime, was reflected finally across line M to end up down here. If this angle is 58 degrees, how far did this rotate from start to finish? Close. $58 and $58, 116. Okay? But this looks like more than a 90-degree rotation, doesn't it? No, but from the start to the finish. So they measured this and said that this is a 58-degree angle. Okay, so if we reflect something across a line and then reflect it again across a line that intersects with it, and their total angle measure between those 2 lines is 58, then the whole reflection to begin from start to finish is going to be double that angle, 116 degrees. Okay. More than 90, less than 180, we can all see that, right? Okay? How much more? It's a total of 116 degrees. Okay? All right, your assignment is on page 204. It's on the bottom. Okay? 3 through 18, 25 to 29, 37 to 42.